back to Electronics 101 Foundations of Circuits and Components. In the previous episode, we explored currents, voltages, and the basic laws that govern all circuits. Today, we move one level deeper into the actual components, the types of signals they handle, and the materials that makes electronics possible. So let's begin. Capacitors. So capacitors are everywhere in electronics. They are inside filters, power supplies, your audio circuits, radios, you name it. A capacitor is essentially two plates separated by an insulating material called a dielectric. It's just two plates. And its job is simple, to store electric energy by holding a voltage across its plates. So that is the interesting part of a capacitor. It can hold charge. The key thing to understand is current flows in a capacitor only when voltage is changing. If the voltage is constant, like a DC battery, the capacitor eventually behaves like an open circuit. So this makes capacitors perfect for blocking DC by allowing only AC signals to pass. Capacitance is measured in farads, but real capacitors are usually microfarads, nanofarads, or picofarads because 1 farad is quite huge. It's basically the amount of charge. Then the next components that come into play is inductors. So if capacitors resist changes in voltages, inductors resist changes in current. So if you remember from our previous episodes, voltage was about the pressure. If you remember the analogy of a water pump, the amount of pressure you put in is more or less voltage. Current is the amount of water that is flowing through a pipe. So capacitors resist changes in voltage. They resist changes in pressure. Inductors resist changes in current. So they resist any changes in the amount of current that is flowing. So an inductor stores energy in its magnetic field whenever current flows through it. Because of this, it opposes rapid changes in current, making it a natural partner to the capacitor. Inductance is measured in henries, and it's a name of a person. And inductors show up in filters, power converters, motors, RF circuits, everywhere. So together we have resistors, which resist flow of electricity, capacitors, which can hold a charge, and inductors. They all form passive circuits. They absorb current, like low pass filters, high pass filters. These are the components that shape and control a signal. You basically control the three aspects: voltage, current, and resistance. Now let's look a little bit into what is an AC signal. So most of the world's information, audio, video, radio, everything, this rides on an AC signal. AC is alternating current. Unlike DC, which is a constant current, AC signals vary with time. So it is like a smooth, continuous waveform. So the most important one is the sine wave, which is a smooth, continuous waveform. There are other AC signals as well, but the one that is of most interest to us is the sine wave. So why do we prefer it? It's incredibly easy to generate, transmit, analyze, consume a sine wave. Power systems, radio communications, and even the audio, they all rely on the sinusoid waveforms. Then we have square waves, which flip instantly between high and low levels. So square wave is like it's at the top at a minute and instantly it drops to the bottom. Then it goes to the top, drops to the bottom. Perfect for digital electronics. A true square wave has a 50% duty cycle. It's like the amount of time it spends on high and the amount of time it spends on low. And then we have triangles and sawtooth waves, which appear in music synthesis, audio, control circuits, timing, those kind of systems. So every AC signal is defined by a few simple parameters. There is a period, which is the time for one full cycle. If you look at a sine wave, it starts here, goes to the top, falls to the bottom, then comes back to zero. So that is one full period. And then we have frequency, which is the number of cycles per second. So which is basically the number of up and down movements it can make within a given second. That is frequency. Then we have phase. This is the position of the waveform relative to a reference. I'm talking about all the simple measurements we usually do on an AC signal. When somebody asks you to measure an AC signal, you look at the period, which is the time for one full cycle. You look at the frequency, which is the number of cycles per second. Then you look at the phase, which is the position of the waveform relative to a reference line. And then we also have RMS voltage, which is the effective DC equivalent heating value. We'll come to that at some other point. So these parameters lets us analyze and compare real world signals very easily: frequency, period, and phase. Now let's look at, we talked about capacitors, we talked about inductance, which are usually found in transformers, and then we talked a little bit about what type of waveforms are available, and AC was a common waveform that is used. Now let's look at materials. There are some materials we need to modify the flow of current or one of the parameters of current. Every electronic component is built from one of the three materials. Either it's a conductor, which allows electrons to flow, or it's an insulator, which resists electrons to flow through that, or a semiconductor, which has a strange semi-permeable behavior. So let's talk about semiconductors. I mean, how can you make a material semiconductor? Either it's a conductor or an insulator, right? How can it be semiconductor? So conductors like copper, silver, they allow electrons to move freely. They make great wires. If you open up a household wire, you're going to see copper or silver in that. And then we have insulators like glass or mica. They hold electrons tightly. They block current. They don't allow it to pass through. So even rubber, if you are wearing rubber shoes or slippers, you are very much insulated from electric shocks on the ground. And then we have semiconductors. This is an area of interest for us as part of our series. So this is silicon. It sits perfectly in between. Semiconductors are special because their electrical behavior changes depending on the energy of their electrons. So if you remember how electrons are placed, they are in valence bands around an atom. So let's talk about it. So these are called energy bands. The valence band holds electrons bound to an atom. So if you think of an atom's nucleus, around that we have all these electrons which are in specific bands. So the interesting thing about electrons is they jump only between the bands. They don't take any other in between place. That's an interesting behavior of an electron. And then we have conduction bands, which holds electrons that can move and create current. So there are valence bands and some of them are conduction bands, the ones at the edge, which allows the electrons to move and create current. Then there is the band gap. This is the amount of energy needed to jump from one valence band to a conduction band. So if the gap is small, the material conducts very well. If you just give it a little bit of energy, the electron jumps into the conduction band. But if the gap is large, the material becomes an insulator because you need to give it a lot of energy to make it actually push the electron into the conduction band. Now comes the game changer. We talked about semiconductors, right? There is a concept of doping. Let's talk about what doping is. Pure silicon doesn't conduct much. But if we add just a tiny amount of impurity atoms, we can dramatically change how it behaves. This process is called doping. And it's basically what allows us to create diodes, transistors, IC, entire microprocessors, all of it. So this tiny impurity changes the behavior of silicon where it starts conducting. How much of impurity we add depends on what type of a component we are trying to create. So there are two types. P types, which is basically a trivalent element like boron, which creates holes, and the N type, which is the pentavalent element. You need to go down deeper to understand this, but basically P type creates holes, N type it adds free electrons. Just remember that. P type has holes as majority carriers, N type has electrons as majority carriers. So if we add an impurity, the silicon will have holes to carry carriers, or the silicon will have extra electrons as majority carriers. Almost all modern electronics, including the phone or computer you are using, they are built on clever arrangement of these P type and N type materials. This is where true electronic begins. So that's a really high level overview of the building blocks of modern circuits: capacitors, inductors, AC signals, and semiconductor material. In the next episode, we'll start bringing these together to form real components like diodes, transistors, and we'll try to understand how they shape every electronic system around us. So stay tuned. If you like the series, do subscribe, drop some comments if you want me to talk about something in more detail, and let's continue exploring the world of electronics. So come back for the next episode. Thank you for watching.